Sorry? What did you say? Much earlier time step. Oh, okay. Right, okay. Oh, right. And let me also inspect is the numerical dissipation added the correct way. So Fi is Ti minus T2. And so the Fi is going to be subtracted from T1. Right, so the contribution from T1 is subtracted from T1, so that seems to be right. And the contribution from T2 is a minus sign in Fi, which then gets added to T2. So this is this seems to be correct from this. If the normal is pointing inward, can you say again?
Yeah, when you check if the normal is pointing inwards, just change the UI type.
Right.
But also I think it will affect the index.
Oh, it'll affect here. Is that what you're saying? Affect the.
Yeah. So with this code, you are assuming that the next y and pointing upwards. If it's not the case, you should not apply it.
Right. Okay. So this when I compute this interface flux, so I'm computing the flux towards the normal direction, no matter if the normal is pointing outward or inward. So if the normal is pointing outward, then I should be, yeah, if the normal is pointing outward, I'm computing the flux outward, which means I should be subtracting. If the okay, you are right, so I have to be subtracting anyway. So this is if the normal is pointing inward, then I'm actually computing the flux inward, which I should still be subtracting. Okay, so this is actually correct. Divide by normal magnitude, square root. And you see here is also okay. So let me try again on this computation. Let's try to 0.07 to see if it's actually let's actually make it a movie for I goes from 1 to 100, and let's say actually let's back up our W0, and every time we want to integrate for a little bit, So let's do this, and W0 and FEM plot TP W and 1 to 500, and do we sleep for a little bit? Okay, so let's actually do axis equal and sleep, and then we set our W0 to W and color. Oh, I should be using pause as opposed to sleep.
Also, you don't really figure out the time, so you might want to close them.
Am I creating a figure every time? No, I don't think this one didn't create a figure ever. What? Yeah, I'm gonna be solving ODE every time. So I want to see a movie of this. So I should be using what? Pause? Okay. Right. Okay. So that seems suddenly this thing didn't work anymore, right? Let me do it again. Close. And I think I forgot to have axis equal. And I'll be doing this. Okay. Yeah, looks like the water is bumping into the wall, and when it reflects back, the solution over here starts to diverge. Right, okay. So let's see if it can be remedied by increasing the amount of numerical dissipation. So this is ADT 2D, and if I remove the divide by 2, would it work for a bit longer? So let's do this. The same thing, right? So it stopped over here. And yeah, the same phenomenon that prevented the previous code to work seems to be happening over here too. So again, this seems to be like a shock resolving issue that similar to what we have encountered last time. But this time I don't see it's the numerical dissipation term being wrong. Or is it? Oh yeah, the numerical dissipation term is wrong actually. Sorry. So the flux is actually the size of the flux is already multiplied by the size of the normal. So and actually instead of dividing by the normal magnitude over here, I should be multiplying by the normal magnitude over here, right? So this is because when the flux here, when I add it to the flux is already multiplied by nx and ny. So the speed should be actually the speed multiplied by the size of the normal. So okay, so let's go back to our divide by 2 and run the code again.